Oh, funny. Let's do a little mindfulness though, if you wouldn't mind, just to settle in, make the transition, and then we'll get rolling. I'll grab my pens in a minute. All right, just sitting up straight and coming into this place. It's okay. Just get done what you gotta get done. Okay. It'll be there when you're done. The voices begin. All right, my friend. So, I got your homework, Hannah, last week, right? Okay,
yeah.
cool. Is there a My Open Math
There's
floating about?
not. Well,
There's
we
not.
finished it on.
Oh, we finished it,
was
cool.
there was only 2.3,
Yeah,
correct?
it was already finished.
Awesome. Yeah, I was gonna open up some stuff, but we need to talk first, so let's get rolling. This is where the calculus truly begins. Like we've kind of been working around the edges, but today we're really gonna get into the derivative. So let's just do a recap and then add some notation. And there is a My Open Math on section 2.5. My Open Math, Mom, 2.5. This is the biggest assignment. It's almost as big as all the other assignments put together. So what I'm gonna recommend is don't try to just like rip through it, because it's broken into sections, and we're gonna cover it all and we'll work in class together. I think the due date I have for it currently is next Wednesday, but if we need more time, we'll take it. Because I really do think it will take that amount of time to get through the material. So I would say here, go slow. After today, you can probably do, the first 10 or 15 problems after today. But there's like 40.
Is that including like 2.3 and 2.4
Is
in there?
we're kind of skipping.
Or I
some-
guess we did, 2.4, we did 2.4.
Yes, 2.4 we kind of already did, just not officially. I'm gonna open with an intro that basically does 2.4 for us.
So this is the only one?
Yes.
It's not gonna be, okay.
Yeah, exactly, yeah. So 2.3,
Done.
we did, yeah, and then 2.4, we've kind of already done. And we're gonna do it right now. So actually, let me ask you a question. I've got this cost function. So I've got a cost of producing Q items is 3,000 plus 15Q. Oh yeah, Mace, you're really in the hot seat today. This is gonna be fun. So, I don't, what's that?
God damn it, Jack.
Yeah, I don't think Jack's coming today. I don't think Jack's gonna show up to save us. Jack might have had a good thing, St. Patty's Day. Who
I didn't
knows?
hear from him, so.
Oh boy, sounds like the best of ones. And then C is the cost in dollars or whatever. So here's a quick question. We've seen this kind of thing before. What is the marginal cost?
3,000.
That is not the marginal
15.
cost.
One
yeah,
of
one of those
I wonder
two.
which
One of
one
those
it
two.
is.
So this 3,000, this is the fixed cost. This is the cost we can't get away from, even if we produce nothing or sell nothing. 3,000 bucks just right up front, overhead and those kind of things. The marginal cost is equal to 15. And then that's got a unit on it. It's dollars per that making sense? Mace, how's that feel for you?
Pretty solid.
Solid, yeah? So if I want to find the cost of producing 100 units, I just simply let Q be 100, and that'll give me the result. This marginal cost, what does that represent business-wise? We've talked about it just a little, but what does that represent in the business world? When we talk about marginal quantities, what does that mean?
The difference between like one additional item.
Yeah, beautiful. Yeah, very nice. Very nice. You're smoking it. So the marginal cost is equal to the increase if we, the increase in C if we increase Q by 1 unit. Very nice. And marginal things are always going to be of that nature. It's the amount of change in the output given a change of 1 unit in the input. This is pretty straightforward. Now that we've seen this and we reviewed it, I could give you any formula like this. I could say, the cost is equal to 2,500 plus 2.5 Q, and I could ask you those same questions, and now it'd probably be easy. What's the marginal cost? 2.5. We just look at that and grab the slope, right? So this marginal cost is also the slope of the cost curve at our point of interest. Well, since this is a line, it doesn't matter where I'm at, the marginal cost is the same. If we sketch this thing out, C and Q, it looks like this. We intersect right at 3,000, and it probably doesn't even make sense to have a negative part on there because we don't have negative quantities. But the slope of this is 15, and the slope of that is the marginal cost, and it doesn't matter where you're at. So we've seen this, done a little bit with it. What if I gave you this cost function? So what if now the cost function for producing Q units is 3,100 plus x squared minus 20x. Now, if I said to you, what's the marginal cost? It's not quite so obvious. When I have a linear oh, sorry, this should be Q here too. Sorry, maybe you were looking at that, Hannah. I'm wondering. Yep, I thought so. I thought so. So thank you for looking at it just the way you did. And this should be Q too. There's also Qs. These are just Qs. Sorry. So, for example, the cost of let's see, 10 items would be 3,100 plus 10 squared minus 200. And so what do we got here? 3,100 plus 100 minus 200. So just 3,000. No. Yeah. Yep. 3,000. But what is the marginal cost? If I bump up by 1, so if I increase Q by 1, how could I figure the marginal cost at that point? What could I do? So what is the marginal cost at 10? In other words, what is the increase if we bump up by 1? How could we do this problem? So what is marginal cost at Q equals 10? I'm going to sketch a graph of this thing out. In fact, if we did a little parabola work on this, this is actually 3,000 plus Q minus 10 quantity squared. And once I have it in this form, I can figure out where the vertex is. The vertex is going to be at 10, 3,000. And this parabola opens upwards. And I have something that looks like that. It's unreasonable, and if we didn't know that, we could get a graphing utility out and figure it out. So the point that I'm asking at is right here. And to find an approximation to that cost, I could move over to 11, find the cost of 11 units, and then just find the difference between these two values. I don't quite know what it would be at 11, but we could figure it out here really quick. So the cost at 11 units is going to be 3,000 plus 11 minus 10 is just 1, so 3,001. That's not the marginal cost though, that's just the actual cost, right? So the marginal cost is approximately the difference in these two. So approximate, and I'll explain why I'm saying approximate in a second. Approximate marginal cost is going to be C, cost of 11 minus cost of 10. And that's going to turn out to just be 1 for us.
Would it be, is the 3,000, should that be 3,100 at the top? When you factor
Up
in
top.
Right here?
Yeah.
Or here?
Yeah.
Oh yeah, thank you.
So it would just be 1 on
Yes
1, I
ma'am,
think.
yeah, thank you.
It's not a big difference.
It is, it matters though. This doesn't change luckily, but thank you. Yes, thank you. Thank you for being the precise eyes. I need a person like you around in my life. I need people to help me with the fine detail. I'm not a fine detail guy.
That's alright.
No, it's good. That's why we need all different kinds of viewpoints in the world. So yes, thank you, Hannah. So we'll fix that up. So that is an approximation to the marginal cost. It's actually also the slope of the secant line. So the slope of this line turns out to be the rise, which is 1 unit over the run, and that's approximately our marginal cost.
So theoretically, if we had 2 points on that parabola, could we also just find the marginal cost and find the slope of this?
We can find an approximation to it because in business, anytime we use this term marginal, we're actually looking not at these big spreads between 2 points. What we're really looking for is the slope of the tangent line at a particular point. So true marginal cost is the slope of the tangent at that point. And what is that slope? Mace, let me ask you that. So right at 3,000, what is the slope of that tangent right there? This line that I just drew. 0. Got a minimum, does that make sense to you too, Hannah? So the true marginal cost is 0. So let's put up a couple of pointers here. So true marginal cost is determined by the slope of the tangent line to the cost curve. And we want a way to get at that as easily as we got at that here. So now check over here. The slope never changes here. It's just a constant thing. So no matter where I go and I say, what's the slope of the tangent? Well, the tangent is just the same line. There. So in a line, marginal cost never changes, or marginality never changes. But over here, look at how it can really change. If I just drop back a little bit to like maybe 7 units, look at that. I've got a negative marginal cost at that point. Over here, I've got a positive marginal cost at that point. So what we're going to talk about today is how, and for almost the rest of the semester, how do we get at that given this? So if I gave you this and I asked you the question, what is the marginal cost? And we'll answer this question today. At Q equals 7, units. Really challenging to answer by looking at that. I could do an approximation of it. I could find the cost of 8 units and 7 units and find the difference like we did. But what I really want is this true slope right here. I want that true tangent slope. So the way to get at that is with the derivative, and we've been talking about that. We're gonna talk about it more. Do you see an eraser anywhere?
In the little thing.
Yeah, let's, good eye. Thank you, sir. So we're gonna spend, you.
Oh, now that's an eraser.
That is foul. Hold on, let me see if I can find something. There's a one off of. Okay, I got one. I bummed one off of a friend. Better. Ish. Better? I have to teach in this room all day. This is grim. I heard that WD-40 is a really good thing to rub all over these boards.
WD-40 is just like the best thing
It
alive.
is. You seem like a guy who might have some on him.
Oh, I definitely do. have
Not
to-
in that bag,
No, no, in my car I definitely.
Okay, really?
Yes.
Okay. It'll smell like somebody spilled gasoline in here, but that sucks. Okay, cool. So let's refresh what the derivative is, and also get some new notation. So we're given a function and a formula. So just a formula, f of some variable. We defined the derivative. Have I used this notation? Have I used the prime notation? I haven't used any of that notation. Okay, well,
You've used the colon above that.
this guy like this? Let's stick
It
with.
was on our homework, wasn't it?
Oh, maybe so. Maybe so. Yeah, yeah. So we'll use this. So the derivative of f is written like this. I read this as f prime. That's how I would say that. Of x. And it is defined by the limit as h goes to 0 of f of x plus h minus f of x over h. And we've seen that. Let me refresh your memory what the hell that is. So this picture should be in your mind when you're thinking about derivatives. Let's do a little curve. Let's pick a point x. X plus h, if h is positive, that's to the right. H could be negative, we draw it that way often. Hello. And so the slope of this line right here is this quantity. So this is f at x plus h, this is f of x. And what I'm finding here is the change in output over the change in input. So right here, this is delta f, and then this is just delta x, which is also just h for us, just h units. This is the thing that I use to approximate the marginal cost over there. I let h be 1, and I found the secant line. Remember, this is the secant line here. That all sound familiar? Yeah, the terminology. And what we do is we're going to let h, when this says limit as h goes to 0, that means we're letting this interval shrink, letting these 2 points move together. And then this point rides along the curve, and when they meet, we have the tangent line. So we approach the tangent line as h approaches 0. Just imagine that point. They're like little beads stuck on a wire, and there's a line connecting them. Just let them slide together. And as they coalesce, we get that tangent line there. I've told this story a couple of times. Is that making sense, or should I talk about it a little bit more? Happy to. Feeling okay about this, Mace? And Katya, I know you're coming in, warming up. Okay, cool. So I want to introduce some new notation. So this is a process. Just realize this is a process. That the derivative is the end result of this process that I just drew up here. So other notation for this, f prime of x, I'm going to put triple equals, just saying equivalent to, sometimes we write d dx of f of x out front. Our book, so this is or, our book uses this capital D of f to just mean the derivative of f. If you just remember this D stands for derivative, you're good to go. If I know y is equal to f of x, then I might write y prime. And that signifies the derivative of f. So today, we've talked about this a little bit, we're really getting into it today. Today we're going to start developing formulas that allow us to crank this process out with a type of algebra that you've never done before, but it's very simple and kind of amazing. So I'm going to do one, you kind of have to pay this, oh my God, that sucks. So fucking bad, oh my God. And maybe, let's try this. Let's see what happens with this guy here. Okay, we got it. That's better. That's pretty good. I'm gonna look like I work in the coal mines by the end of the day, which is kind of normal for me. Let's get this shit all cleaned up. And Katya, you might want to just check out the first 15 minutes of the lecture. There was kind of an intro to this that will make a lot of sense in retrospect. Okay, so we need formulas for finding the derivative, because we don't want to go through this limit process. I'm going to do it once, and you're going to realize, God, I don't want to do that every time. So we pay this one up front, we don't do it again. Then I just kind of give them to you. You can kind of believe it. So here's an example. Find the derivative of x squared, good old x squared. Gonna happen a lot. Actually happened in the example with the cost function I gave earlier on. So what this means is I'm gonna go to this definition. Limit as h approaches 0. So this is my f of x. F of x is the function x squared. So in other words, f of whatever is that thing squared. That's how that works. So when I write, let's just write it out. F of x plus h minus f of x over h. So now I'm going to write out, this is limit as h goes to 0. X plus h is going to go in this box. So it's x plus h quantity squared. And then f of x is just x squared. Cool. And then all over h. Let me stop for a second. So we want to work this through. I'm going gonna FOIL out x plus h quantity squared. So this becomes limit as h goes to 0. When I FOIL this out, it's x squared plus 2xh plus h squared, and then I had minus x squared again over h. How's this look? Mace, let me know when you're cool with this. Cool with it, all right. So the x squareds cancel. And what I'm left with, you've seen this a couple of times, just not a lot. I'll just rewrite out what I have. Now remember, what is the first step in doing a limit? What's the first thing you try?
Plug.
Plug and hope. Hope we're not dividing by 0. If I replace h with 0, unfortunately I get 0 over 0. It's the top, when I replace h with 0, I got dead over dead, got 0 over 0. This is actually good news because it means I can do something, I can factor and hope for the best. And notice that I can factor an h out of the top, so this is limit as h goes to 0, pull an h out over h. Does that look cool? Check that out. And then the h's cancel. So I'm going to cancel those beasts, and now I'm back to this. Now I've just got that. Mace, what happens when I just replace h with 0 there?
You just get 2x.
Yeah, beautiful. Yeah. So when I actually evaluate this limit, now when I plug, I don't have any division by 0, everything's cool. So check this out, we've got our first formula. The derivative of x squared, so here's f of x, here's d dx of f of x. The derivative of x squared is 2x. Now I'm gonna just show you what if we had done x cubed and see if you can catch the rhythm that's happening here. So if we had used x cubed instead, its derivative turns out the same process, exactly the same. If you ever feel like doing it, you can find it. So that's a 2 there. It's a very, very fancy 2. It got super fancy all of a sudden. And then the derivative of x to the 4th would be 4x cubed. Can someone maybe hazard a guess at that one? What's the rhythm?
5x to 4.
Yeah, how'd you do that, Hannah? That's perfect.
It's whatever exponent, it seems like it's the coefficient, and then as the derivative goes up, it's like goes up in a exponent from the previous one.
Or goes down. Yes. Oh, yes, like that. Yes,
Sorry,
yes,
that
ma'am.
one,
Yeah. So
or goes down from.
yeah. So from the original, check it out. Look at the rhythm. Bring that. You look sad. You look sad, Mace.
I just accidentally bit my lip.
Oh gosh. Okay. I was like,
No,
I'm
I get it.
characteristically sad.
No.
I'm glad you're not sad. This is good. Thanks, and thanks for letting me harass you. I appreciate it. So you bring the exponent out in front and decrease the exponent by 1. This is our first rule. It's called the power rule. So let's put it up in big, bold form up here. And then let's do some practice with it. And this is what's going to be able to help you knock out a few of those first homework problems. My God, what did they do to this thing? Bruh. Okay, so our first rule, the power rule. For differentiation, if I take the derivative of x to a power, I bring the exponent, the current exponent comes out in front, and the exponent that was goes down by 1. The power rule. So, let's do a little practice. What's that derivative? We'll start out chill. Got a couple tricky ones coming.
10x to the 9.
10x to the 9? Yeah. So what you're learning right now is a new method for manipulating things. This is a calculus, a method. This is differential calculus. The techniques we're learning here are like the algebra you've learned long ago, but brand new. That's right. Is this looking cool? Think about what is amazing here. What we actually just did was this crazy limit. So actually what we found, by simply moving the exponent down, we did this with great ease. Just moving the exponent out in front and dropping it by 1. That accomplishes this. And that's the thing you can keep in the back of your mind, that wow, that turned out really beautiful. That's ridiculously beautiful. So now what if I were to ask you something like this? The first step is to convert it into x to a power. To use the power rule, you've got to have everything in this form. Katya, my friend, what power, if I rewrote this, what is the power that x should be written to give me this thing here? How do you get things to flip? What kind of exponents turn things into fractions? Yeah, you're right.
Be -1.
Beautiful, thank you. Yes. I know that was a lot of stress and unexpected, but you
I was trying, first I was like, where would the 1 go? Because I kind of assumed it was negative, but then I just have to reorganize.
You did great, thank you. It was cool, it was completely unexpected. But you're performing under pressure. No doubt a key attribute of a business person. So, can we just do this real quick? And then, could you do this and rewrite it as a fraction? Take a minute. What does the derivative of this? Just follow the rhythm. Practice the new rhythm. You don't even have to think about it as much. Just do it. And then the rewriting it as without a negative exponent, that takes a little bit more. And I'll start cleaning the board. It's going to be my main job today, apparently.
But you said do it and then flip it back to.
Yes, ma'am. Yeah, rewrite it as a fraction. Does that make sense?
Yeah.
Okay. Feeling good on this one, Mace?
Like I have, like I'm pretty sure I know the derivative.
Let's do that part. Let's start there.
So would it be -1x, -2?
Absolutely. And I'll just put it as a negative sign, but it is -1 times x to the negative second. Perfect. Beautiful.
I just don't know how to put it back.
That's okay, man. You just did calculus. So
Yeah.
congrats. Good job. Could someone help me? One of my 2 other friends. How do I rewrite this as a fraction?
It'd be like 2 over x, but I think there's a negative somewhere. Maybe.
No.
1 over -2x.
That's we're getting there. We're getting there. It's sure 1 over some. And let's just leave the negative. So how about -1 over, what's the exponent?
-2.
It's -2. So when I flip it under, it becomes x squared. So we were almost right there. And maybe I don't know if this is what you were saying, Hannah, but it didn't sound
No.
like it.
it's not.
Okay, cool. Little tip. If I have x to the negative, some positive number, That's just 1 over x to that positive number. Little reminder. So we see that. So let's do a couple others. What about first we have to write that as a power. Just to get us rolling so we're all on the same page, could someone help me rewrite that? What power of x do I have here? What's a square root?
Is it 3? I don't know.
It is not.
Okay.
But I appreciate you trying.
2.
It is related to 2, but it is not 2. If I have, what'd you say?
1/5.
Yeah. Yeah, 1/2. So if I have the nth root of x, that's x to the 1 over n. Little thing to, good, useful. Clearly we should write this down, I would say. So for example, the cube root of x is x to the 1/3, and like Mace just told us, when there's no number in that pocket, it's a presumed 2. So it's x to the 1/2. So step 1 is to get it as a power of x. Now let's find that derivative. And then the challenge I'm going to ask you is rewrite it without a negative exponent, because it will have a negative exponent when you take that derivative. Yeah, that's beautiful. Yeah, really nice. Not yet. Yeah, okay, cool. I'm glad you're finally getting challenged in the class. This is great. A happy day for me.
Still working.
Still working. So, step 1, write it as x to the 1/2. Then do the rule. What's the rhythm for finding a derivative?
It's the exponent.
Exponent comes out front.
Exponent up front, and then
There you go. Then put x. There you go. And then subtract 1 from the exponent. And that's your new exponent. I'm going to write that up here. Is that how you spell?
Yeah.
No, that's not right, is it?
There's an E between H and M.
Well, I don't think there's an E in
There's
it. Is
an
there?
R.
There's another Y.
There's another Y or an H or something. Can we look it
RH.
up?
Looking at it. I
RHY.
can't even. I think
It is RHYTHM.
I was gonna say. Wait, no.
R-H-Y. Okay, got it. Like that. Thanks. Okay. Well, we all learned some spelling today too.
That's like when you know how to do it, but then you're like looking at it, you're like, wait, what?
Right.
I was thinking about run.
Yeah. Yeah. That definitely. Yeah. Power rule rhythm is move the current exponent to the front. 2 is decrease the existing exponent by 1. Maybe when I say is the current, what I mean is current. This could get confusing here. So when I do that one up there, I bring the 1/2 up in front. So that's 1/2 x, and what's 1/2 minus 1?
Negative.
-1/2. Yeah, exactly. So that's beautiful. That's 100% correct. And then we got the negative exponent. So Katya, is this sounding okay? Yeah? Okay, awesome. So now I could bring this, a negative exponent allows you to go underneath. So I'm gonna, Hannah, you'd left the 1/2 on top, completely legit, but we could also just bring that down with the 2 like that.
Oh, okay.
And that's exactly the same thing you had, it's just like less fractions within fractions.
Yeah.
So that's our derivative. Right on, friends. I'm gonna just hope and pray. Let's do one more. Okay, challenge mode. This is the boss fight. Derivative of 1 over x to the 1/3. Step 1, write it as x to a power. What is that? Then proceed. Things are going. Okay, so the 1/3, beautiful, but you didn't decrease the x, so the exponent's kind of gone, right? Because 1/3 minus 1 isn't just nothing.
Yeah.
What's 1/3 minus 1?
2/3.
Yeah, close. 1/3 minus 1 is going to be a negative number, negative 2/3. So that's our exponent, negative 2/3. Does that make sense? Okay. And then you can convert that into, if you want to bring it underneath, but that's the derivative, and there's nothing wrong with that.
Yeah.
Yeah, make sure is there a negative there? Yeah, okay, cool. How's it going? Yeah, beautiful. That's lovely. Yeah, good work. And then how would you turn that into something without a negative exponent? What would it look like if we did that? Get away so there's no pressure. How's it going over here? So that, I love that. What's that exponent right there too? So how did that happen?
I don't know.
Because I like everything else.
1/3. Oh. Yeah, this, does that just make it 2/3?
Yeah, it's just 2/3 in the bottom. Yeah. And I think now I just caught something. So that was, actually for this one, that's negative 1/3. That's, yeah. And then did I catch that on yours, Scott? Yeah. Let's see, because I think I might not have. So this is derivative of x to the negative 1/3. That's, we missed the, because that's a, x to the 1/3 would just be x to the 1/3 with no fraction, but that's x to the negative 1/3. So sorry about that, I didn't catch that. Does that make sense? Let's write it out together. X to the negative 1/3. Yes, ma'am. No, just not 1 over. This is the 1 over form, and then, you see what I'm saying? it's just plain old x to the negative 1/3. Yeah, beautiful. Now we do the rhythm.
Oh,
Does that make sense?
yeah.
Kind of, yeah, okay. Well, let's go through this one together. So this is x to the negative 1/3. I think we're all in agreement with that. And then the rhythm. Negative 1/3 comes out in front. X to the, and I'm just gonna write it out here, negative 1/3 minus 1. Partial credit for sure. Now I just have to subtract 1 from negative 1/3. What is negative 1/3 minus 1? How many thirds?
-2 thirds.
Good guess.
Fourth.
Negative 4/3, yeah. So check this out. You're gonna combine these fractions. This is negative 1/3. Convert that into thirds. It's 3/3. So it's negative 4/3, like that. So my final answer is negative 1/3 x to the negative 4/3. We're just gonna need practice, that's all. New stuff. Does that make sense? Katya, you're good? Yeah, okay, cool. And then if I was gonna rewrite this as a non-negative exponent, I'd just say negative 1 over 3x to the 4/3. The thing you don't wanna do, and you're probably gonna do it at some point, is just take the derivative of the bottom and leave it there. This is a classic mistake. So, classic mistake, let me just point it out, is that you see that down there, and then you just go, oh, it's 1 over 1/3 x to the negative 2/3, and you do that all in the denominator. That's not the same thing, right? Like clearly these two are not, there's a 4 in this one, there's no 4 in that one. So this is not the way to go. You've got to first go to x to a power. This is the only time you can use this rule. No fractions, nothing. All right. We're almost at a point where we can answer our very first question about the marginal cost. But we need a couple rules for how to do fancier things. So for example, if I had, what is the derivative of x squared plus x cubed? I can do each piece separately. How do I do them together? And that's where these rules come in. So rules for combining derivatives. And we're just gonna go with the most simple ones today. If I ask you to find the derivative of the sum of two things, put whatever you want in the box in the triangle, just take the derivative of each piece and add those. So it's kind of like it distributes. Derivative of that plus derivative of that. If there's a minus sign in there, no worries, do the same thing. Usually I would write these separate, or together, but I'm gonna just put them separate to be really clear. If I have the derivative of a difference, it's the difference of the derivatives. And then the last one for today, every day we're gonna come in and boost this up a little bit more. Yeah, it is exciting, exactly. No, it is, you were just excited, it was a guttural response of joy.
It definitely has nothing to do with yesterday.
Yeah, nothing at all, nothing at all. Kudos to you for being here. So, if I have the derivative of a constant, so like a number times something, I can pull that constant out in front. You just bring the constant out in front and then do the derivative. So let me give you a nice example. If I asked you to find the derivative of 2x cubed minus x to the 7th. Let's just do that together. We'll go through together. eventually you're gonna do this really quickly, but I'm gonna go very slowly at first. This is, that 2 is just a constant out front, so this is twice the derivative of x cubed minus the derivative of x to the 7th. And could we just do that together, please, and then simplify and see where you get? I just wanted to show you how to get here, but you can do both those. I've seen you. And then simplify when you're all done, combining all front constants together. Okay, here's a little thing to keep you going, Mace. I'm gonna let us out a little early today.
I just need to get some food in me, honestly. No.
Okay, okay. Okay, my nurturing nature is I want to feed you.
Trust me, I really appreciate it, but I need to get through and I can get some
All right.
some crusty old calf pizza.
There you go. And you don't want that vegan shit that I load that bag up
absolutely
with.
not. No, I'm joking. I would take it.
I know you would. All right. How do we feel about that?
Pretty solid.
Pretty solid?
I didn't bring the 2 over to make it 6x squared.
What did you do?
I just
left it like 2 times 3, which that's cool. Like eventually you'll want to just bring everything together, make it pretty. But if you got here, power, outstanding. Kati, you feel? I like that. That's a solid nod. You feeling okay about it? All right. Let's go back to the example I asked at the beginning. Actually, let's do something a little simpler. Let's do a problem. Find this. We're going to apply this stuff. Find the slope of the tangent line to y equals x cubed minus x squared at x equals 3. So first off, I'm going to sketch this beast out. So it's got a 0 at 0, it's got a 0 at 1, and it's going to look like this. And that should actually go right through 1 right there. So this is what this function looks like. And what I'm asking is, what is the slope of the tangent way out here? So there's 1, 2, 3. It's crazy. I'm going to actually make it look a little less steep. I'm curious about what is the slope here? Slope of the tangent. Answer, it's going to be pretty steep. But what is this slope at x equals 3? Right above that, at the tangent line to this curve, what is its slope? No way to answer that without what we just learned. Because the tangent slope, so here's the thing, and I've said to keep this equivalence in mind. Tangent slope equals derivative. That is going to get you a million miles. Tangent slope and derivative, same thing, equivalent things. So first I have to find the derivative. So step 1 is find the derivative of the function. Find the derivative of x cubed minus x squared. Could you do that, my friends? In fact, I know you can. Would you do that? It's a better question. What is the derivative of x cubed minus x squared? What'd you get, Hannah?
3x squared minus 2x.
3x squared minus 2x. We feel good about that? So the answer is 3x squared minus 2x. This is a formula for finding the slope of the tangent anywhere you want. So let's write that up. So now we can find the slope of the tangent at any x value by evaluating the derivative 3x squared minus 2x at that value. Incredible. We don't have to do derivatives. We don't have to redo this computation every time. We've got a formula. And I asked to find it at 3. So at x equals 3, this becomes 3 times 3 squared minus 2 times 3. So that's 3. What, did you get it already?
Yeah, I'm
What'd
pretty
you
sure
get?
the answer is 75 altogether.
75. That sounds a little big.
But it's.
Can you tell me how you got that? How'd you get that?
Yeah, 3 times 3, 9 squared.
Oh, you're doing it to the 4th.
Okay.
You squared again. So this was great right here, Mace, and then that
21.
21. Yeah, 21. Hella steep. Not as wildly steep as yours. That was big ass steep. Does this make sense? So that is the slope. So this line has a slope of 21. For every 1 unit you go over, it rises up 21. That's crazy steep. Just gonna stop and let that settle in. That's a lot for one day. So at this point, you could, if you wanted, and I would recommend, I'm gonna actually call today because I kind of want everybody here as we push forward, because this stuff's new and it's gonna get a little heavier every day. So what I would recommend to you, friends, is try the first few homework problems, just between now and Wednesday, for your own sake. Get in there and just try a few, especially the ones where they just ask you to find the derivatives. I forget what problem number it is, but just practice this and let it ingrain inside you. You'll be really grateful.
The homework just dropped, by the way.
Oh, perfect. Yeah, awesome. Homework's now open. So let's call it a day. Let's let Mace get some food.
Thank you guys. Appreciate it.
Yeah, you're welcome. It's a gift from all of us to you. If you want, if you're interested in hanging out working, I'll stay here with you. But I'm gonna end the lecture right now. And then our friends who are missing today, one of whom told me she'd be missing, so I hope you played well. Other folks, I don't know where you're at. Hope you watched this video. You're gonna be grateful if you did. You're gonna be sorry if you didn't. Bye.